All right, so the topic of surds is a very important one and one that must be mastered in Year 9 and 10 and quite often in Year 11 and 12. If you recall back to Pythagoras' theorem and if you have a look at this question, okay, if you follow all the steps, when you're trying to find the hypotenuse, it's x squared is equal to 7 squared plus 3 squared. Therefore, x squared is equal to 49 plus 9. Therefore, x squared is equal to 58. And then you said x is equal to square root 58. That's how you get rid of the squared on the left-hand side. Now, normally in Year 8 mathematics during the Pythagoras topic, you would simply punch in the root 58 into the calculator and write down your answer. However, in the surds topic, you'll be expected to take these surds sometimes and actually simplify them without using calculators. So you need to be good at the topic. Now, it's very important to keep in mind that in mathematics, we have real numbers, okay? We have real numbers in mathematics. And then real numbers can be either made up of rational numbers or irrational numbers. So what's a rational number? A rational number is any number that can be expressed as a fraction or decimal. So if you look at whole numbers, okay, whole numbers can be expressed as a fractional decimal. Like if you've got the number 7, you can write it as 7 over 1 or 7.0. Integers like minus 10, that's a rational number. And of course, any fractions or decimals, okay? And irrational numbers, we have surds. You see all these surds, root 2, root 7, 3, root 5, root 21, they're irrational. These are also irrational. And pi is irrational as well, as is E. E is something that you will focus on later on in mathematics and in more advanced years. But, I mean, students have asked me in the past, pi can be expressed as 22 over 7. So the fact that you can write pi as 22 over 7, well, remember that 22 over 7 is a fraction, and that means it's rational. Well, not really in this case, because 22 over 7 is an approximation for pi. It's not entirely true that pi is equal to 22 over 7. If you punch pi into your calculator, it will be a decimal that just will be ongoing. And so that's why, even though in some of the topics like measurement, you can replace pi with 22 over 7, it's really an approximation. So the key thing here that you need to take away is that surds are irrational numbers. All right, now, having a look at this workbook, when is a surd expressed in its simplest form? What I'm asking you is, if I give you the question, simplify 10 over 100, okay? If I give you that fraction, if you simplify that to 5 over 50, what you've done here is correct, but that fraction is not in its simplest form, not until you write it as 1 over 10, okay? So when do you know if you've simplified a surd completely? Well, you know when the number inside the square root is as small as possible. And you're going to see what we're talking about in a few minutes. Now, the next thing to keep in mind is when we are trying to simplify surds, we are looking for these numbers over here. We are looking for these numbers over here. These are our critical numbers. Actually, not 1, because 1 goes into everything, so forget 1, okay? So if I forget 1, we're actually looking for these numbers over here. 4, 9, 16, 25, 36, 49, 64, etc. What's the reason we're looking for those numbers? They're called square numbers, okay? Well, it's because I know that if I square root a squared number, if I square root 4, I just get 2. You see what's happened? The square roots disappeared. Square root 4 is 2. Square root 9 is 3. Square root 16 is 4. Square root 25 is 5. Square root 36 is 6. Square root 49 is 7. And square root 64 is 8. Okay? And so on and so on. So if you square root, what's the next one? 81. Okay? If you square root 81, okay, square root 81 is 9. Now, what's the reason? Well, the reason is very simple, okay? Because, you see, if I have square root 81, that's exactly the same as square root of, instead of 81, 9 squared. And we know in maths that the square roots and the squareds cancel and you end up with 9. Now, there's no need for you to show this working out here. I'm just simply showing you why root 81 is 9. So we are looking for these square numbers. They're very important. So let's see how we're going to apply that to our questions. Simplify square root 8. So what you're going to do, so we know that 8 is not one of the squared numbers, okay? What you're going to do is you're going to try and find two numbers that multiply to give 8, where one of the two numbers is going to be in this category here. So what are the numbers going to be? Square root 4 times square root 2. Okay. Now, out of these two, one of them must be simplifiable, and this one is. Square root 4 is equal to 2. That's 2. The root 2 stays. You can't do anything about that. So our answer is going to be 2 root 2. That's complete. Our next one, square root 75, is find two numbers that multiply to give 75, where one of them is a perfect square, and they're going to be 25 and 3. So root 25 is 5. And that's now complete. The next one, don't be too concerned if there's a number in front, like the 2. We're going to rewrite the 45 as that. And we haven't touched the 2 alone. We haven't touched the 2. But now the root 9 becomes 3. Okay, remember that root 9 is the same as that. And now the square root and the squared cancel and you get 3. So going back to the question, the 2 hasn't been touched. The root 9 becomes 3. And the root 5 can't be simplified anymore. Okay. All right, so now these are further practice questions. So the first one is simplify root 12. I mean, ask yourself, what are the factors of 12? 12 can be rewritten as 12 times 1. 12 can be rewritten as 6 times 2. Or 12 can be rewritten as 4 times 3. Let's look at this now. So, which factors are we going to choose? Is it going to be these two, or these two, or these two? You're definitely not going to choose the first one, okay? Because that's not a perfect square, and 1 is a perfect square, but we never use that. Remember when I said up here, ignore the 1. We never want to use that one. Let's look at the next two factors. So 12 can be rewritten as 6 times 2. That's not a perfect square, and that's not a perfect square. In other words, you can't times a number by itself to give you this or this. Or 12 can be rewritten as 4 times 3. okay? That's going to be our answer, because what's going to happen, you're going to rewrite the 12 as root 4 times root 3. And root 4 is equal to 2. So now 2 times root 3 is 2 root 3. And you're finished. See, if you had tried some of the others, you would never have gotten anywhere, right? Let's have a look at the other ones. See, if you had written root 12 is root 12 times root 1, that doesn't help you. If you had written root 12 as root 6 times root 2, that's a problem, because this can't be simplified and this can't be simplified. So you haven't achieved anything. But our last option, root 4 times root 3, root 4 is 2. And you're complete. Okay. Next one, root 27. Root 27, okay, is, let's have a look. That one there can be 9 and 3. Now, root 9 is 3. So that's our final answer. Root 200. Next one, 6 root 18. Again, if you look at root 18, can you do root 6 times root 3? No, you can't. Because that's not simplifiable and that's not simplifiable. Can you replace root 18 with root 9 times root 2? Yes, you can, because root 9 is 3. So, if we go back to the question, 6 times root 18, which is exactly what that is, you rewrite the root 18 as root 9 times root 2, which is 6 times 3 times root 2, which is now 18 root 2. 98, let's have a look at 98. You can rewrite that. Okay, now I'm quick at these because I've been doing this a long time, but it's going to take you a bit longer than me, obviously, to try and find out the factors. Because, you know, as the numbers get bigger, the factors do get a little bit trickier. So it's going to take you a bit longer than me, but I know that this is going to be 49 and 2. Now, root 49 is? Next one. This one is going to be... If you notice in all of my working, if I just zoom out a little bit, notice how I always like to write the one that simplifies first. Because when this simplifies to a whole number, I like having that at the front of the surd. See? I wrote the root 4, then the root 17, because root 4 is going to simplify to the 2. And that stays as it is. Continuing on now, root 7n squared. That's fine, it looks complex, but it's not. We rewrite it as root 7 times root n squared. The root 7 cannot be simplified. So it stays. And now the root n squared, as I mentioned before, the square root and the squared cancel. Be careful here to make sure that the square root does not extend across over the n, because the n is a whole number, is on its own now without the square root. Question 8, we're going to break it up into root 8 times root x squared. Quite often when I get numbers and pronumerals inside a surd, I like to break them up like this. Now what I do is I focus on breaking up the root 8 into its factors, and root x squared is just going to be x. So let's focus on that root 8. Okay, so the root 8's become root 4 times root 2, which becomes 2 root 2. Okay. Question 9. All right, let's have a look here. So again, as I mentioned before, what we're going to do here, we're going to rewrite this as root 16 times square root x to the power 4 times square root y to the power of 6. Now, the root 16 we know is just 4. Root x to the power 4 is really that. And root y to the power of 6 is really that. You see what I'm looking for in these? I know that the square root and the squared are going to cancel. So I'm always looking for that squared, okay, in both of these. Okay. So I know here the square root and the squared are going to cancel. So what's going to happen now, this is going to be 4. This is going to be x squared. And this last one is going to be just y cubed. Because again, if you have a look at what we discussed, the square root, okay, the square root and the squared eliminated each other, and you see what's left, just the y cubed. Question 10 now. I simply break it up and then I start focusing on breaking down the surd. Okay, so what numbers multiply to give 56? It's funny because, 56, you've got 8 and 7, right? That's not a perfect square, and that's not a perfect square. So you actually can't use 8 and 7. So what I advise you to do is to get out your calculator and start doing trial and error, okay? And in fact, the numbers are going to be 4 and 14. This one's a tricky one, okay? It's trickier than it looks. If you go back to the beginning of the book, I asked, how do you know that a surd has been completely simplified? Well, you should always look at your answer and ask yourself. So if I have a look at this answer, I ask myself, can this be broken down anymore? Are there any numbers that multiply to give 14 where one of them is a perfect square? And the answer is no. Okay, right? So if you look at the factors of 14, okay, 14, they're 14 and 1. That's not going to be of any use. 14 can be rewritten as 7 and 2. That's not going to be of any use, right? That's not a perfect square. That's not a perfect square. That's not a perfect square, and we'll never use 1. So you can't break that down anymore. All right, so that concludes simplifying of surds. And, you're not going to watch what I've done in the last 15 or 20 minutes and be an expert or be very good at surds, simplifying surds. You must pick up your pen. You must practice questions. This introduction to simplifying surds was simply to give you enough information so that you can start doing the questions on your own. And where most students have a problem with this topic is they don't focus enough on simplifying the surds, which is what we've discussed at the moment, before starting the next section. You must be absolutely excellent at simplifying surds before moving on. And I can relate that back to fractions. If you can't simplify fractions, the rest of the fractions topic becomes a problem later on in maths. Because when you get answers, you won't know whether you've done the questions correctly or not. So please make sure you spend a lot of time on simplifying surds and you perfect it before moving on to the next section of the topic.